The mechanical properties of engineering materials are one of the important design considerations that we may use in this design course. So today let us try to understand how these mechanical properties are derived or obtained, and what are the basic mechanical properties that we must understand. We basically use standard tensile test to get variety of mechanical properties and strengths, and later we will be using that in design. So we use a standard dog bone specimen of circular cross section, which follows the standard BAS standard. In fact, BAS standard is very much similar to ASTM E8 standard. In that standard, the details of the specimen preparation until documentation and reporting are clearly specified, and we must follow that strictly. Only then our properties will be accepted and can be used in design. The standard basically tells about the way in which the specimen has to be prepared, what for different cross sections. So you can use circular cross section, rectangular cross section, or a sheet specimen also. So when the cross section changes, obviously the estimated properties do change. So in order for the properties to be consistent, the standard says that you must maintain the ratio, the gauge length of the specimen divided by root of cross section is equal to a constant. That constant usually 5, 11 and so on. It is specified in the standard. So if L by root A ratio is constant, be it circular cross section or rectangular cross section, then the properties obtained will be consistent from the standard tensile test. So we use this dog bone specimen, standard dog bone specimen, and the next thing that standard says is that the speed of testing in terms of stress rate, strain rate, or the crosshead speed, right? Usually it is 0.5 to 1.5 mm per minute for steels. Okay, so that is the crosshead speed we maintain and to obtain the properties, and the way in which the extensometer has to be mounted onto the specimen, right? So all those details are specified, and once you get the data, how to process it, right? The load is usually we get load and deflection data from the standard tensile test, and that has to be converted into stress strain data, and then you plot it, right, to get this. So this you would have seen often in the previous courses, and you know very well about it. So this is a typical stress strain curve of mild steel. You have an initial linear portion followed by an yield point, and then gradually the stress increases until ultimate point, and then you then it falls down and fractures. So this is the typical stress strain curve, engineering stress strain curve. And you also have true stress strain curve, where the stress will increase even after the ultimate tensile strength. Okay, we will see why is it so very briefly later. And we will discuss each of these points, right? What is elastic range? What is plastic range? What is this capital E? What is this PL? This is proportional limit. What is EL? See here in this figure, PL is below EL. Is it correct? We don't have answer for this, because PL and EL are very closely situated. In fact, no one can determine it exactly, because measuring elastic deformation, they are very small strains. Elastic strains are very small. To measure that, you need a highly precise extensometer, which is very difficult to manufacture. But here, for the purpose of understanding, it is kind of exaggerated, and it is mentioned here. Elastic limit, and Y is yield point corresponding SY, yield strength. We use SY. Okay, please look into the notations. And U is the ultimate tensile strength, or just tensile strength. S suffix ut, and then F is the fracture point. See, some materials, in this case, the mild steel clearly has an yield point, so we take it. But there are some materials which will not have yield point. So in such case, we use offset method. What do? We take an offset strain, 0.2% of strain, that is 0.002, located on the x-axis, and then draw a line parallel to the elastic portion where it will, until it hits the stress strain curve, the corresponding intersecting point is the yield strength. We will look into now these properties. It is a kind of recap. Engineering stress. It is actually the resistance of the material, right? Uh, intensity of force per unit area, in fact. Intensity of resistive force per unit area. Original cross section, in fact, we take the original cross section, that is the one before deformation, where P is the applied load, A suffix O is the original cross section. Engineering strain, change in length by original. L0 is the gauge length. So you must understand clearly the concept of gauge length. So in the figure it was mentioned L0, right? It was at the central portion of the specimen. Gauge length, why do we mark it? What is the purpose of it? So you have to understand the concept of Saint-Venant principle for this, but I will leave it to you, that part. See, if you look at the dog bone specimen, it has a shoulder and right, for gripping. The diameter is very large compared to the specimen diameter, right? And there is a taper from shoulder to the specimen diameter. There is a taper. You will have a fillet. Because we have a geometric discontinuity here, there will clearly be stress concentration. So when you pull it, actually, you will have stress concentration in the area of shoulders. See, for us to apply the definition of engineering stress, right? All the fibers, imaginary fibers of the circular rod, must be pulled equally. Okay. So that is not possible in the shoulder region. So why we are locating L0 somewhere in the central portion of the specimen, right, where all the fibers will be subjected to uniform deformation. And what is the distance of this gauge length from the shoulder? That is also specified in the standard. Or you can go to your any mechanics of solids books having the concept of Saint-Venant's principle. The distance would have been specified, probably 2 times the diameter or 3 times the diameter from the shoulder. The effect of stress concentration will be minimal, right? So this is something about the gauge length. I don't want to get deeper because the concept of tensile testing can itself be offered as a separate subject. Okay. So L0 is the original gauge length and L is the gauge length after deformation. We focus only on gauge length. Proportional limit, it is a point on the stress strain curve where the stress is linearly proportional to strain. See, these are very, very important concepts. It might look very simple to you. You may be complacent in understanding these properties. I urge you to, recollect it very seriously, because we will be using this in design of various machine elements in the 2 courses. Okay, so the meaning it should come to your mind the moment these properties are uttered, because when you look at the numbers, you must be in a position to interpret it, for which you must know the meaning. So the proportionality is known as Hooke's law, right? So E is equal to sigma by strain, stress by strain. It is basically a measure of the stiffness of the material. Okay, so elastic limit means actually it is a point on the stress strain curve where you will not have any permanent deformation. That is, upon the application of the load and its removal, the material will come back to its original position. Yield strength. See, there will be a point on the stress strain curve where the strain begins to increase very rapidly without the corresponding increase in stress. That point is yield strength. Okay. In fact, the material will start entering the plastic zone. So as I said earlier, not all materials will have obvious yield points, like except steel and alloys of iron, particularly brittle materials like okay, and other brittle materials. See, for example, aluminum, copper, they may not have clear-cut yield point. We use that offset method. So I've showed in the previous slide like how to get an offset line. A strain of 0.2%. It is not constant. 0.2% is not same for all the materials. Okay. So for each material, you have an offset strain, which is derived based on the experience from the laboratories. Okay. So sometimes it could be 0.1% or 0.1 or 0.5 also used. So you can see here, locate that offset strain here on the x-axis and draw a line parallel to the elastic curve until it is the stress strain curve, and the corresponding stress is actually strength. Ultimate tensile strength, it is the maximum stress that the material can sustain before breaking. So in fact, you will start to see necking soon after it attains this point. So you would have seen like one dotted line and one continuous line falling down in the stress strain curve. So the one which falls down after the ultimate tensile strength point is engineering stress strain curve, and the one with dotted line is actually true stress strain curve. See, what is that true stress? How do you get it? See, in fact, as we load the specimen, the area constantly decreases, right? So strictly speaking, we must use the instantaneous cross-sectional area to measure the stress experienced by the specimen. So that stress is actually, we call it as true stress, right? Load by instantaneous cross-sectional area. Similarly, strain also incremental strain. Because the gauge length keeps changing, right, as you deform. So you must use this thing, this definition, sum of all the incremental deformations. Then the another important property is ductility. What is this ductility? The tendency of a material to deform significantly before fracturing. It undergoes severe plastic deformation. So when a material fails, it gives us a warning so that we can take any precautionary measures so that the material will fail safely. Ductility. Brittleness, yes, you will have little or no plastic deformation in general. See, it is not that we are ignoring elastic deformation. Elastic deformations are very, very small. In fact, they are less than 1% of the total deformation. Okay, so we don't usually consider it. How do we measure this ductility? This is very important property of the material we use in design. So we use this, you would have done your laboratory testing, right? Ductility measurement, percentage elongation, percentage reduction in area. After the specimen fails, you would have measured the final length, final diameter, right? Percentage elongation is actually the ratio of change in length or increasing length of the gauge section to the original gauge length expressed as a percent. Similarly, percentage reduction in area, ratio of decrease in the cross-sectional area of the specimen after fracture, very important, to the original cross-section expressed as percent. So this formula is very important. Then some of the important properties we must know. What is that strength? In general, strength is the ability of the material to resist external force, okay? But it is actually the maximum resistance force that the material can exert before fracture is strength. Okay. Stress and strength, you just remember, see, stress is also resistive force, strength is also resistive force, but strength is the maximum stress that the material can withstand. So how do we measure strength? Based on the different types of stress that is induced by different types of loads. See, a material can be subjected to axial load, bending load, torsional load, or combination of these loads. Accordingly, we have bending strength, torsional strength, shear strength, compressive strength, when it is subjected to compressive force, and tensile strength, yield strength for tensile loads, and so on. Elasticity, we had seen that elastic range, plastic range. What is that? See, when we subject the material to the forces well within the elastic limit, it will regain its original shape. What is happening at the atomic level? See, and it is very, very small. As I said, it is less than 1%. In fact, if you look at the real stress strain curve, the elastic curve will be almost close to the ordinate of the stress strain curve, that is stress axis. It is very, very difficult. In fact, you have to zoom in to see the elastic portion, that linear region. Okay. So during elastic deformation, the atoms are actually originally displaced from their positions, from their original positions, but they will not take up new positions. That is why when you remove the load, they will come back to their original position and take up the original shape. Plasticity, here the material will retain the deformation, permanent deformation, right? So in this case, what happens is the atoms are permanently displaced from their original positions, and they will take up new position, and hence why upon the removal of the load, it may not be able to come back to its original position. Stiffness or rigidity, it is again the ability of the material to resist deformation for the applied load. So lesser the deformation, higher the stiffness. We use modulus of elasticity as a measure of stiffness. Then resilience is another important property used in the design of springs. You will be studying this in design of machine elements too. It is the ability of the material to absorb energy when deformed elastically, right? And it will release its energy when unloaded. So a resilient material will absorb more energy within the elastic region. So higher the resilience, higher the energy that it can absorb the shock. For example, in case of springs, it is measured by a quantity called modulus of resilience, which is the strain energy per unit volume. So how do you measure it from the stress strain curve? It is actually the area under the elastic limit. You can see that here. This is actually the modulus of resilience. Another property is the toughness. It is actually the total energy that a material can absorb before fracture. Okay. So this is highly essential for components to withstand impact loads. Tough materials will basically can be bent, twist, or stretched significantly before failures takes place. We measure it by modulus of toughness. So from the stress strain curve, it is actually the total area under the stress strain curve will give the modulus of toughness. Okay. Very important property is the hardness, where you have relative movement that we will see. It is basically the resistance of the material to penetration or permanent deformation. So in general, it could be resistance for abrasion, scratching, cutting, or shaping. Okay, that is what, when you have a relative movement between two parts in a machine, like in pinion and gear, cam follower, and so on, like in bearings also. Uh, the material must have enough strength, right, to withstand to perform its function without any loss of material. So in such case, hardness is an important property. How do you enhance the hardness? Right, by case hardening, surface hardness process. So we have different methods of measuring the hardness, but we will look into some of the standard methods: Brunel hardness test, Rockwell, Vickers, and then Shore scalar scope. In the first three methods, an indenter is used. Indentation hardness methods, they are all indentation hardness techniques. You apply a specific force onto the specimen, measure the area of indentation or diameter or depth, whatever, and then express into some quantity. So the shape of the indenter will be ball, pyramid, or cone, and they are made up of very, very hard material, particularly harder than the specimen being tested, like diamond, tungsten carbide, or any other hardened steel. So Depending on the cross-sectional area and depth of indentation, hardness is expressed as an empirical number like Brinell hardness number. In case of a shore oscilloscope, the height of rebound from the surface is expressed as the hardness, dynamic hardness. So the first three methods are static hardness, and shore oscilloscope is a dynamic hardness. So therefore, as the hardness of the material increases, the strength also increases, and hence the wear resistance too. So for certain materials like steels, researchers have already developed some empirical relationship between strength and hardness. You can right away use that in design. For example, ultimate tensile strength is is equal to 3.5 times approximately the Brinell hardness number. So this you can use it if you know hardness, what is the tensile strength. For most steels, this empirical relationship can be used. Okay. So these are the important properties you must have at the tip of your fingers, and you must be able to visualize them the moment it is uttered, and you must be able to interpret the values of these properties as and when it is needed during the design. So please don't underestimate the significance of these mechanical properties, because you will be using data books. Data books specify these properties, so you must be in a position to select appropriate mechanical properties and hence the material required for your design. So these are the references that these contents are being borrowed from. Thank you.